Thanks for weathering the storm, I would say, and coming here in this early hour to listen to my presentation. I hope it's going to be worth it. And today I would like to share with you some insights, a little bit from a hardware perspective in what are the challenges that we are facing to deal with some of the requirements that are coming towards us from the world of artificial intelligence, but to a certain extent, of course, also the world of high-performance computing. And, we all know that AI is kind of really becoming a major technology for all of us. And the way I look at AI, it's not just a technology that will allow us to do existing problems better, solve them in a more efficient way, or it's really being able to start doing things that we couldn't think of before, right? We have all seen in November, I think, the announcements of like ChatGPT. I mean, even this morning I read an article in the New York Times that the New York schools now have special methods to kind of grade papers that are submitted by students, because students have to write their papers now in the classroom, so that they cannot just use ChatGPT to generate papers. Even writing code, you all have heard of GitHub Copilot, so there's definitely, we're getting closer and closer, I think, to what people refer to as the Turing test, right? Where you start kind of getting the impression that machines are getting really intelligent. And actually, I did try, when I knew I was going to give this presentation, and then I heard about ChatGPT, I'd actually typed in the prompt from write a keynote for an AI conference. And so this is what I got, actually, and literally, I'll read it. Good morning, everyone, and welcome to the annual conference on the latest developments in AI. And as we all know, AI technology is constantly evolving and changing. So you can read the rest for yourself. But, it's, in the future, you don't need to invite people anymore to come and give these keynotes. You just type in whatever you want to have a topic to be discussed, and ChatGPT will give you some reasonable answers. So clearly, it's amazing what's becoming possible. And now, this is, of course, a little bit more of a mundane application, but really there are very important, life-changing opportunities that are now being created with AI technology, right? I mean, if you think about in the biomedical field, in 2020, for example, Google AlphaFold was actually they created a breakthrough for the 50-year grand challenge in computational biology to kind of define the structure of folded proteins. And that created an avalanche of follow-up research, follow-up results, to now, a little bit more than 2 years later, basically almost all the structures of all proteins have been identified, right, leading to tremendous opportunities in the world of science and medicine and the like. So clearly, the impact that we see that this technology gets to our life is just beginning, and it's really fundamentally changing, what kind of problems we can solve. It's not only about, some of these very big life science problems that we are talking about. In AMD, we have a big project which we call Pervasive AI, and that refers to the fact that AI is showing up everywhere in all the applications that we see, not just the cloud and the enterprise data centers and so, but in retail, in transportation, in the digital home. And in all of these settings, you need a tremendous amount of efficient compute, but the figures of merit and the requirements and the tools you have to leverage AI are all a little bit different. And that's why you, for example, see if you look at the product portfolio of a company like AMD, you see a whole plethora of technologies that are kind of being leveraged in all these different applications to introduce AI solutions in this world. Now, having said that, this comes, with a lot of challenges. And as we are here as a research community, it's probably good to not only tout the horn of existing solutions, but also highlight, what are the challenges that are ahead of us, especially if we extrapolate, the current trend that is happening in this world. And I have clustered it around 3 topics, and let me go through them one by one. The first is the requirements from a compute, energy, and data manipulation perspective. Many of you probably have seen this slide. If you look at the last couple of years and the evolution of the compute requirements for the neural networks, you see that in the last 10 years, every somewhat between 3 to 4 months, the new networks are requiring about twice the amount of compute than the previous one. Now, if you compare that to the early days of Moore's Law, where we were kind of really excited about doubling the capabilities of a chip every 18 months, and by the way, that's a long time ago. Now it's more every 2 years, if at all. You clearly see that this is a pretty spectacular exponential trend that is going to be challenged to be maintained, and it's coming with a lot of also opportunities, I think, for new inventions and new technologies. The other thing is the sustainability. I have a reference here to an article where Facebook talks about what one AI training cluster consumes today. It's about 6 megawatt. If that cluster is, they actually predict that the next generation will be probably tenfold of that, more than 60 megawatt. For training, an AI network. If you kind of extrapolate that over the energy usage over a whole year, that's somewhere in the ballpark of more than 500 terawatt hours per year. Now, that's the equivalent from what the energy consumption of Germany is, these days. So clearly, if you think about it, this is another challenge. It's not only, trying to provide the compute capabilities as we extrapolate some of these requirements, but also doing it in an energy efficient way is the second problem. So we have to make sure that the energy footprint of the AI training clusters and so is going to be much more efficient. And then the third aspect is, of course, AI relies a lot on data and on the parameters for the networks and so on, and especially driven by the latest evolution in transformer networks, driven by recommender systems and natural language processing and so on. You see also there an exponential growth in the number of parameters and the data that is being that has to be handled, and that comes also from an efficiency and from a hardware perspective with its specific challenges. So, and then the final thing is that we always talk about compute, and as I just showed you before, data is becoming a very important aspect. When you look at the characteristics of these networks, They also vary quite a lot, and they are evolving. This is what we in the hardware world call a roofline model of a specific hardware architecture, which is characterized by the shape of the red curve. And then what you do is you put basically different neural networks and their characteristics on that diagram, where the vertical axis talks about the absolute performance that is required, whereas the horizontal axis talks about the I/O requirements that required, which is characterized by how many operations per byte of data that you download on your hardware does this algorithm requires. And the more you go to the left, the more I/O bound your algorithm is. The more you go to the right, the more compute bound your algorithm is. And so what you see is that architectures, typically what you see is that the right horizontal curve is moving upwards. The vertical dotted line is moving to the right. So more and more the existing hardware architectures are limited in their capabilities of handling complex neural networks because of their I/O limitations. In other words, it's not in AI about peak performance. It's about a combination of efficiently moving your data around and doing the compute of the data. You have to be able to feed the data into the compute platform. And so peak performance is becoming far less of a relevant number in AI. So that's one cluster of challenges that are coming with the hardware. The other one is that when you look at AI and the deployment of AI, you have to take into consideration, both the constraints of the edge and the cloud. In today's world, I would say the very traditional way of working is that you have this large compute infrastructure that does the training of your networks. And then once you have your network trained, you kind of port it onto an edge device, which is a lot less expensive, has less compute capabilities, but can be deployed in settings in the field. And there is, some inconsistencies between the two architectures, the one in the cloud where you train your network and the one in the edge where you are deploying your network. But ultimately, what you really would like is that when you look at a solution where AI is an essential part of the technology to enable the solution, you should be able to look at it as a combination of cloud infrastructure together with edge infrastructure. And you would like that ultimately the system does not necessarily always have to go to these separate phases of training in the cloud, deployment in the edge, training in the cloud, deployment in the edge, but rather kind of a cooperation between the edge and the cloud. And a good example of that is, for example, federated learning, where what you typically do is you have a trained network, and then you start to deploy that onto millions of devices potentially in the edge. And then as you deploy them at the edge, every edge device is learning about how to improve the network. Let me just take a simple example. I mean, you have a face recognition, for example, application, and you deploy it on your phone and you find out that it doesn't really work well for your personal situation. And it doesn't recognize some of your pictures and your face on these pictures or something like that. You would like that the local device is basically learning from that situation, but rather than sending the data back to the cloud, just send the updated parameters of the network back to the cloud. And if the cloud then gets, out of all these million devices, the updated parameters, it doesn't have to go through the whole retraining with the whole data sets that you otherwise would have to send back. It also is helping with privacy. You don't really send the data back to the cloud, you send parameters back to the cloud. It helps with bandwidth issues. If you have 1 million devices that all send all their data back to the cloud, that's a big load on the network. But if you can avoid that by just sending the improved parameters back, so you can have far less of a stress on the networking bandwidth. So that's a good example of some step in the direction where you look at solving a problem, leveraging AI in a holistic way, where you have a role for the cloud and the edge, both in the domain of training and deployment. So that's important, that we understand that when in the future we are developing solutions, we are taking into account the fact that we have cloud infrastructure and edge infrastructure, and we have to optimally leverage these two infrastructures. Now, that comes with a challenge, because one of the interesting things is that, as we all know, of course, the major rules of algebra, like things like associativity and so on. But one of the challenges that you have is that when you're dealing with real data types, you know, associativity is not really a true characteristic of your computation. So if you look at the formula on the bottom, when you're dealing with data types that are restricted in accuracy, you know, the two formulas on the bottom are not necessarily yielding the same result. And that has consequences, because sometimes you will execute the same algorithm in a different way on two different architectures. You might have an architecture in the edge, a hardware architecture in the edge, which is driven by the limitations that you have in the edge, which is the cost, which is the power consumption, which is other sometimes figures of merit that are important in the edge. And you have your infrastructure in the cloud, where you assume that you have a lot of horsepower, and these two architectures of these two compute platforms might calculate the same algorithm in a different way and yielding different results. And that's a challenge. So if you look at, for example, very specifically, you know, when you look at a kind of a matrix operation or something like that, as you see here, the top is you know, the formal way of presenting it. The left is, for example, the way how you would implement it on an edge device, a small device, where your loops are organized differently than on the right, where you have a device that is deployed in the cloud, where you have much more compute resources available, and you would do your tiling potentially might be different in how you tile your loops over your hardware. Your data types might be different in how you implement data types in the edge versus the cloud. And as a consequence, you will see inconsistencies. But if you're thinking about a total solution where you combine these two systems, you have to find ways in how you can do that. And that leads us, and I will come back to that later, to the need for coming up with a unified architecture that can scale well, you know, between cloud and edge, that has similar characteristics, but that can also cater to the specifics of the cloud and the edge. A good example of that is, you know, for example, you know, it's not just about performance and throughput. It's also sometimes about latency, especially, you know, in the edge. You know, latency is important. If you, for example, deploy an AI algorithm on the brakes of a car or something, automatic brakes or so, you definitely would like that brake is happening with as low latency as possible when something has been detected. That might be less of a relevant issue in the cloud. And so you can have, for example, an algorithm that runs perfectly well on the edge. Now, if you would run that same algorithm on the cloud with the same characteristics, you probably, I assume, you have a much more powerful chip there, has much more compute capabilities. Now, if you want it to behave exactly as it is in the edge, you're going to underutilize it. So what people do is they are trying to parallelize as much as possible in the cloud, right? By parallelizing, what you start doing is you're going to use your hardware more efficiently. You're going to have bandwidth improvement. But because of the data parallelism that you introduce in a traditional cloud infrastructure, is you will introduce latency because you have to batch your data. You have to first kind of load your bases, then you fire off all these different compute engines, and then you get results. So every time you have a latency, which makes that if you do the function in the cloud, although you have much more powerful hardware potentially there, if you want to use that hardware efficiently, you're creating a behavior that is different than if you would deploy that algorithm in the edge. And you know, that's one of the challenges that if you want to come up with a unified approach between cloud and edge, you have to take into account. So this is a little bit shown here in this slide, right? Where if you think about cloud, in many cases, the hardware in the cloud is developed, the hardware platforms in the cloud are developed typically to deal with transactional functions that have to be executed as fast as possible, that rely on scaling out compute resources, that you throw a whole bunch of compute resources at it. So that's a typical hardware thinking of the cloud. In the edge, it's very different. You know, first of all, things like power restraining sometimes what you can do. You have requirements like real time. I mean, if an algorithm is running faster than it's supposed to run, it means you're wasting power. So it has to run just fast enough. An algorithm in many cases on the edge has to run deterministically. You want, if you hit the brake, you know, you want to make sure that every time the behavior of that function of hitting the brake is exactly the same. You don't want to have the experience then when you start PowerPoint where sometimes it starts up immediately and the next time, you know, you see the little circle going for a while. You know, latency is of course key in some of these applications. So the hardware on the edge typically has figures of merit that are added or different than what you see in the cloud. So therefore, in many cases, people design the hardware differently for the edge than for the cloud. The other important aspect is that there is no such thing as the ideal characteristic of a hardware platform for AI networks. Once again, you see in this diagram, this is these roofline diagrams where you see the solid curves there, which represent different hardware architectures, and then the different dots and stars and triangles and so on are different neural networks. And as you can see, some of these neural networks are compute bound. It means they're the efficiency of their execution is dependent on how much compute power you have available. Whereas you look on the left on the red circle, these are algorithms that are I/O bound. It means that you're underutilizing typically the compute. You're limited, the performance of your algorithm is limited by the I/O bandwidth that how fast you can feed the data, you know, into the compute platform. So these algorithms are all over the place, and one architecture might, you know, cater really well to one nature of an algorithm. Another architecture might cater well to another one. And then to conclude on these challenges, we are in the very early phases of AI. We all know that. I mean, the bottom right slide shows you, for example, the evolution of paper submissions on some of the major AI conferences, 3 of the major AI conferences. I mean, it's exploding in terms of how people come up with new ideas and new suggestions. Even very recently, there are even, I mean, it's about data types, it's about new topologies, it's about even new training mechanisms. So there's a very active research community going on, and it's really exponentially growing in terms of new ideas and new algorithms that are pretty disruptive from the previous generation. So flexibility of whatever architecture is very important. And that's all why in the AMD we are talking about the era of what we refer to as adaptive computing, which means that future hardware architectures have to be able to adapt themselves to the requirements of the algorithms. So you have basically in your hardware platform, you have 2 degrees of freedom, I would say. On a typical hardware platform, you have the software that allows to program a fixed hardware architecture. In adaptable platforms, you can do 2 things. You can, of course, write software that is implementing your algorithms, but you can also, at the same time, optimize your hardware architecture to the algorithms that you're trying to implement. So you have an extra degree of freedom, and that extra degree of freedom allows you to adapt, for example, the data types that you're dealing with, the data movement that you're dealing with, and the likes. And so that's what adaptive computing is. And then on top of that, there is an extra challenge, is that when you come up with an architecture like that, ideally what you want is an architecture that behaves the same in the edge or the cloud. There might be a performance difference, but in terms of the ultimate implementation of your algorithms, whether you do that on a smaller device, on a larger device, the behavior in the cloud or the edge should be the same. That's what we refer to as a unified architecture that is symmetric over the cloud, and the edge. So say a few more words about adaptive computing. So as I said, when you look at a lot of algorithms, how the data is communicated between the different functions is very much depending on the algorithms in many cases. Arithmetic precision, I talked about data types. Also how the structure, the data structures and how they're stored in the memory is very different for different functions in your algorithm. And then finally, the connectivity with devices, especially in the edge, is very customized. Now, if you have like one architecture and you're mapping these algorithms on that architecture through, you compile them to the architecture, there's always somewhere some suboptimal behavior of these functions on this architecture. So what we try to achieve with adaptive computing is that you can really adapt your hardware architecture such that it can really align itself with the unique characteristics of the functions that at that time you're trying to execute on your hardware. I'll give a few examples, right? I said data movement, for example, is very important. Well, here you see an array of processors. I'll say a little bit more about that later. We call them AI engines. You can have hundreds of these processors. And when I say adapting this architecture, towards the algorithm you're trying to solve, a good example is customizing your data movement. Suppose you're trying to deal with video data, then you will program the communication between these processors in a kind of a pipeline fashion because data is streaming typically in video applications. However, you know, when you have, for example, a training algorithm, you would like that, you know, one parameter, for example, or some parameters are shared amongst different compute elements. So you have more a broadcast pattern of your communication. And so what you can do is you can configure, you know, your interconnect in a way that it kind of aligns with the pattern of data movement of your specific functions that you're trying to implement on this architecture. Another characteristic is, for example, how the memory is organized. You can have a programmable memory hierarchy where you can have different functions that are spatially assigned to different processor blocks. And you can decide for each of these clusters of processors what's the width of your memory access, what's the depth of your memory access, what's the hierarchy of your memory. And so in that way, you kind of create a memory structure that perfectly matches the requirements of the functional module that you're trying to implement. So that's what adaptive computing is kind of the concept of adaptive computing. Another aspect of adaptive computing is data types and the accuracy. What you see here is a diagram where on the vertical axis you see a measurement for the accuracy of the neural network that you're deploying. So the higher, the better accuracy. It means that one means you're always exactly giving the right answer. On the horizontal axis, you basically have a measure for the accuracy of your arithmetic. In other words, you know, let's say floating point will be all the way on the right, integer will be on the left. And so as you have high accuracy, your network generates the right data. And then what you start doing is you start potentially, what in this diagram shows is that for the same network, that's the dots with the same color are the same network, you start reducing the accuracy. We call it here signal to noise ratio. I'm not going to explain exactly how we come to that number, but just assume, you know, lower signal to noise ratio means that you're reducing the accuracy of your data types. And what you see is that for different networks, you can get, you know, with less accurate arithmetic, you can still, you know, get good results for the networks, but it's different for different networks. Now that's important because, for example, if memory storage is important, yeah, as I said, in some cases, you know, algorithms are I/O bound. Some cases they are compute bound. Sometimes they are memory bound in the sense that you cannot store all the data in the memory, so you have to go to remote memory, which slows down your execution. Depending on what is all the different columns are different accuracies, and if you look at the bits per number, you see that, you know, it varies from 19 to 6 for int5, for example. That, of course, is immediately representative for the amount of memory you need to store that massive amount of data that you have to deal with. So if you can get away with a 6-bit number, you will try to do that because you can now deal with much larger networks with the same memory. And so these are examples that you have to really analyze when you decide about the hardware architecture. Now, in AMD, we have implemented this kind of adaptive architecture, and it has a lot of legacy, I would say, from the FPGA world. As you know, I come from Xilinx, which was an FPGA company, and when we got acquired in AMD, we definitely started moving into the the world of compute and processing. And just as in an FPGA, where if you think about an FPGA, for those who are not familiar with it, it basically is a large array of little programmable logic functions. So you have little memory cells that you can program like ANDs and ORs and whatever. And then you have a programmable network that you can program to connect all these logic functions together. It's a pretty simplistic way of explaining an FPGA, but I think it will do it. So we have taken that architecture, the same concept, and we have now, instead of programmable logic, we have now VLIW superscalar processors, which we refer to as AI engines. And we have a massive amount of them, literally hundreds and hundreds of them. And then we have a switch network between all these processors so that you can program the data movement between these processors. And each of these processors, just as in an FPGA, has some local memory. In an FPGA, we refer to that as a block RAM, a little memory block next to every logic function. Here, you know, we are talking about, think about it if you're used to processors, a cache memory. It's not a cache memory, but you know, mentally you can think a little bit about that. Now, this is inherently also a data flow architecture, which means that the data is triggering the execution of functions. It's not a certain function, a certain compute function that, you know, for example, requests data and stalls if the data is not there. Here, this is an architecture that is driven by the data, which is relevant in applications like AI, where data is essential. So this architecture has a lot of advantages. It's scalable. You know, on the left could be an architecture that is an edge device that has, let's say, 20 or 30 of these. You know, for example, we actually recently at CES announced the Ryzen CPUs, the 740, which has it's a client device that has a small array of these AI engines connected to it. And then you have the cloud, where you have a big device that literally has hundreds, if not more, of these VLIW processors in there. And you can map your AI algorithm in an identical way, such that the behavior between edge and cloud doesn't change. The only thing that changes is potentially the bandwidth, but the accuracy doesn't change. The latency doesn't change. The only thing that changes is the bandwidth, which is, of course, less of an issue, you know, for an edge device, because you're dealing with a unique situation, whereas in the cloud, you deal with all the different edge devices together. So that's a big benefit that this architecture gives you. And that goes against a more traditional cache-based architecture, where you get your performance through what we refer to data parallelism. So whereas in the data flow architecture, you get your performance to a parallelism, which we refer to as pipelining. In a cache-based architecture, you get your performance, you know, through data parallelism. Now, if you do data parallelism and you want to exploit the full potential of your hardware, you need to batch. You need to first load your bases with data, and then you fire off all these engines. And that, as we know, gives you this problem that you know, your latency is changing. So the data flow architecture is the red diagram, which shows you how for a bigger device you get more performance, but the same latency. Whereas for a cache-based architecture, what you see is you get more performance with a bigger device, but you also get more latency. And then finally, what's also important is that when you think about a data flow architecture, it also suits very well computing not just on the data in use that sits in your memory, but also computing on data that is in motion. When you look at many applications, especially in the cloud, and you analyze, you know, you have, for example, 1,000 processes that are working together, and you look at the efficiency, you find that perhaps, 50% of the time you're spending on compute, and 50% of the time you're losing your performance in communicating data around in the network. Now, one of the things you can do in a data flow, a compute data flow architecture, is you can do compute as the data is moving through your device, which means that you can also reduce, some of the time that you spend in the networking. So you can, for example, do collectives offloading. You can do inline data compression. You can reduce, therefore, the bandwidth that's on the that's put on the network. And so that's another benefit of such a data flow architecture, that you really can improve not only the pure compute performance. And ultimately, this leads to an emerging architecture where you have a composable data center, where you have accelerators, where you have CPUs, where you have storage devices, where you have compute in the network, in the smart NIC, and ultimately you can create a kind of a scale-out implementation for your algorithm in the data center, where you allocate the necessary resources, where you connect them in a topology that is tailored towards your application at hand, and where you can do the compute at the right places in that infrastructure. So that's what we refer to as the composable data center, enabled by these adaptive data flow architectures. So when you look at all these challenges that we have, and this is, I think, the only plug that I really have about AMD, AMD definitely is very well equipped to cater to a lot of these challenges. We have basically all the components in our war chest, I would say. We have CPUs, GPUs, we have the data flow architectures, we have what we refer to as adaptive SoCs, and we have the smart NICs functionality. Now, I only spent most of the time today on the hardware. I just want to say that one of the key challenges is when you come up with these sophisticated architectures, the software, of course, is becoming so much more challenging. Being able to deal with the complexity and the tremendous flexibility that these architectures bring, and still unleash the full potential of these architectures without exposing the complexity of these architectures is a big challenge. And that's where a lot of work in the research community is going on. And you have different user communities that the software addresses, from the high-end practitioners, which are the people that try to solve a problem, be it in the medical space or be it, and that are typically operating in the frameworks, to the people that we refer to internally in AMD as the performance ninjas. These are the people that are really, trying to get everything out of the hardware architecture, that are building the libraries, that are being leveraged by the higher levels of the stack, and everything in between. Catering to the software for these kind of different groups of people is definitely a very big challenge. And I think in AMD we realize that, and that's also why we're starting more and more to kind of open up to open source and leveraging the community. There is some links here to work that's going on in AMD on the open source. I encourage all of you to look at it and potentially leverage it or contribute to it. And that's open source, on the GPU side, on the AI accelerator side, and on the networking side. As we have a large community of universities here, I would like to also highlight that we definitely recognize the importance of university contributions. And one of the things we noticed is that whereas a lot of the universities in the high performance compute, they have access to these compute centers. Now, these compute centers are run in a very rigid way. You don't want, a student to mess up, your infrastructure. And so one of the things we have done is we created these centers of competence, which we call heterogeneous accelerated compute clusters at 5 universities in the world, which are accessible by other universities. In Europe, we have ETH and Paderborn that are the key places there. And what's the difference with a traditional rigid HPC environment is you can tinker with the hardware. You can decide, you know what, I'm going to try another networking protocol, right? You can take over the infrastructure for a while, and then once you've done that and you messed up things, you know, there is the original image is loaded again and it's made available to other people and so on. So that's, you know, one of these aspects that we felt was missing in the traditional way in how universities can have access to infrastructure for high performance computing. And have a look at that. And of course, we are also supporting traditional HPC centers with donations and software and equipment. So with that, I would like to end with the last paragraph that ChatGPT, because ChatGPT generated a 4-page document for my speech. And so, you know, you can read it. So, and I say thank you, and I hope you all have a productive and enlightening conference. So that's the words of ChatGPT.